At 4:55 in the morning, Pacific time, on September 15th, 2017, a spacecraft that had spent 13 years orbiting Saturn simply stopped talking. Not slowly, not gradually. One moment it was transmitting data, live in real time, from inside the atmosphere of the second largest planet in our solar system. The next moment, silence. Engineers at NASA's Jet Propulsion Laboratory estimated that Cassini broke apart completely within about a minute of that final signal, torn apart and vaporized by the very atmosphere it had spent its final months studying more closely than any spacecraft ever had. It was, by design, a death. And yet buried inside the data it sent back in those final weeks, hours, and seconds are questions that scientists, years later, still cannot fully answer. This is the story of what Cassini actually found as it died, and why some of the biggest mysteries about Saturn came not from its 20 years of careful observation, but from the risks NASA only allowed the spacecraft to take once it had nothing left to lose. To understand why Cassini's final act mattered so much, you have to understand the deliberate, calculated risk NASA decided to take with it. Cassini launched in 1997, a joint mission between NASA, the European Space Agency, and the Italian Space Agency, and arrived at Saturn in 2004, beginning what would become 13 years of continuous observation, nearly 500,000 photographs, and a fundamental reshaping of everything we thought we understood about the ringed planet and its moons. It was the first spacecraft ever to orbit Saturn, and its accompanying Huygens probe achieved the first landing humanity ever managed on a moon other than our own, touching down on Titan in 2005. But by 2017, Cassini was running dangerously low on fuel, and NASA faced a decision. Simply letting the spacecraft drift, uncontrolled, risked it eventually crashing into one of Saturn's icy moons, particularly Enceladus, or Titan, worlds considered among the most promising places in our solar system to potentially harbor life, and contaminating them with any stray microbes that might have survived the journey from Earth's cleanrooms decades earlier. So mission planners designed something audacious instead. Rather than end the mission safely, they aimed Cassini directly at Saturn itself, and along the way, sent it somewhere no spacecraft had ever dared go before, through the narrow, largely unmapped gap between Saturn's cloud tops and its innermost rings. That set of maneuvers became known as the Grand Finale, and it began in earnest in April of 2017, unfolding across 22 separate dives over 5 months, each orbit threading Cassini through that narrow gap before finally, deliberately, sending it plunging into Saturn's atmosphere on September 15th. The risk was real and immediate. That gap between the rings and the planet had never been explored, and nobody could say with confidence whether it was truly empty or whether it was full of ring particles and debris that could shred the spacecraft on the very first pass. Scientists gathered anxiously for that first dive, genuinely uncertain whether Cassini would survive long enough to even begin the sequence of maneuvers that would define its final months. It did survive, dive after dive, each one gathering exactly the kind of close-up, high-risk data that mission planners had spent 20 years too cautious to attempt, because losing the spacecraft early would have meant losing everything else it still had left to give. And what it found in those final months immediately started raising questions nobody could fully resolve. One of the strangest and most persistent mysteries involves something that sounds almost too fundamental to still be unsolved: how fast Saturn actually rotates. That might seem like the kind of basic planetary fact that should have been settled centuries ago, but Saturn's thick, swirling cloud cover means scientists can't simply watch a fixed surface feature and time its rotation the way you could with a rocky planet. Instead, researchers have had to rely on more indirect methods, and for years, competing radio and magnetic field measurements had produced maddeningly inconsistent answers, day lengths for Saturn that disagreed with each other, depending on which method and which decade of data you consulted. Mission scientists hoped Cassini's ultra-close Grand Finale passes, mapping the planet's gravity and magnetic fields in more precise detail than any previous mission had achieved, might finally settle the question once and for all. And the data did meaningfully improve our understanding, but it didn't fully resolve the underlying puzzle. Saturn's exact rotation period remains, even now, an actively studied and only partially settled question, an almost embarrassingly basic fact about one of the most recognizable planets in our solar system, that a fully successful, 20-year, close orbit mission still couldn't pin down with total certainty. The reason it's so difficult connects directly to an even stranger finding buried in Cassini's final data, something researchers at Texas State University and elsewhere have specifically flagged as genuinely difficult to explain. Saturn's magnetic field, according to Cassini's precise final measurements, is aligned almost perfectly with the planet's own rotational axis, off by only the smallest fraction of a degree. According to our fundamental understanding of how planetary magnetic fields are actually generated, through what's called the dynamo effect, churning motions of electrically conductive material deep in a planet's interior, that kind of near-perfect alignment shouldn't be possible. Dynamo theory predicts that a planet's magnetic field ought to be tilted relative to its spin axis, the way Earth's magnetic north pole sits at a real measurable distance from true geographic north, the way Jupiter's own magnetic field is famously tilted and offset. Saturn's field being almost exactly aligned with its rotation axis is, by the physics we currently understand, something that shouldn't be able to persist, and scientists still don't have a fully agreed explanation for why it does. Researchers continue actively studying exactly how Saturn's magnetic field is generated internally, specifically because Cassini's data revealed an alignment that current models struggle to produce. Then there's the mystery of what's actually connecting Saturn to its rings, electrically. Cassini's grand finale data confirmed that some kind of electric current genuinely links the planet to its ring system, a real, measurable phenomenon captured directly by the spacecraft's instruments as it flew through that narrow gap between the two. But researchers studying that finding have been candid about how much remains unknown, openly stating that we're still unsure of exactly how that electrical connection actually works, and that considerably more research is needed before anyone can offer a complete explanation. It's a genuine, documented feature of the Saturn system, caught directly by Cassini's sensors in its final months, and it remains only partially understood years later. Perhaps the most viscerally strange discovery from those final dives came to be known, informally, as ring rain. As Cassini threaded its way through the gap between Saturn's cloud tops and its innermost rings, its particle detectors sampled something nobody had ever directly measured before: icy ring particles being funneled downward by Saturn's own magnetic field, falling out of the ring system and into the planet's upper atmosphere, essentially raining material from the rings directly onto the planet they encircle. Papers published shortly after Cassini's final plunge describe this phenomenon in vivid terms, describing what researchers characterized as a pounding hail of compounds striking Saturn's upper atmosphere, material and chemistry. Researchers hadn't fully anticipated finding in that specific narrow region between planet and rings. Cassini also detected a genuine mix of organic compounds directly within Saturn's rings themselves during this final phase: water, silicates, methane, ammonia, and carbon monoxide among them. And significantly, that chemical mixture differed measurably from the chemistry found on Saturn's own moons nearby. That difference matters because it complicates simple stories about the rings and moons sharing a single common origin, and researchers are still working through exactly what it implies about how and when the ring system actually formed. And that question of age remains one of Cassini's most consequential unresolved legacies. Before the grand finale, one of the ring system's most basic properties, its total mass, remained stubbornly out of reach for two of its three main components. Small ripples stirred up by nearby moons, detectable as light passed through the rings, had already let scientists calculate the mass of Saturn's A and C rings with reasonable confidence. But the B ring, the widest and most substantial of the three, is simply too thick and too opaque to let light through in the same useful way, leaving its mass a genuine mystery for decades. Cassini's final, extraordinarily close flybys were specifically designed to solve that problem, broadcasting a radio signal back to Earth as the spacecraft sailed near the B ring, allowing scientists to measure the incredibly subtle gravitational tug the ring exerted on that signal's wavelength, and from that, calculate the ring's actual mass directly. As Cassini participating scientist Matthew Tiscarino explained at the time, pinning down the B ring's mass mattered enormously because there was, and still is, an ongoing scientific debate over whether Saturn's rings formed alongside the planet itself some 4.5 billion years ago, or whether they're a startlingly recent feature, potentially only around 100 million years old. Cassini's final measurements moved that debate forward considerably, but they didn't end it outright. The full picture of exactly how old Saturn's rings really are and exactly how they came to exist in their current form remains an active area of research that Cassini's death made possible to investigate this closely in the first place, without fully closing the case. Even Cassini's very last images carry their own strange, quiet weight. The spacecraft transmitted its final photographs back to Earth several hours before the actual atmospheric plunge, meaning humanity's last visual record of Cassini's journey was captured slightly before the true end. But even after those final images were sent, even as the spacecraft continued its fatal dive into Saturn's thickening atmosphere, its instruments kept transmitting new data in real time for as long as physically possible, right up until atmospheric forces finally overwhelmed it completely. Linda Spilker, Cassini's project scientist, described the data pouring in from those final grand finale orbits as every bit as exciting as the team had hoped, while candidly acknowledging that the team was still deep in the process of actually working out what all of it meant. That process, by every account, has continued for years since. As Caltech noted following the mission's conclusion, there was still data the Cassini team had to keep working through, alongside the separate ongoing task of passing what they'd learned onto the next generation of scientists who would continue analyzing this dataset long after the spacecraft itself had ceased to exist. What makes this story genuinely compelling isn't a single, tidy, unexplainable anomaly, the kind of thing clickbait headlines often reach for. It's something more scientifically honest, and in its own way, more interesting. Cassini's death wasn't the end of a story. It was the deliberate creation of an entirely new, higher-risk dataset, one NASA had spent 20 years too cautious to attempt gathering, made possible specifically because the spacecraft no longer needed to survive the attempt. And what that final, fatal series of dives revealed wasn't a single shocking secret. It was a whole cluster of genuine, still unresolved scientific puzzles. A magnetic field aligned in a way current theory says it shouldn't be. An electrical connection between planet and rings that nobody fully understands. An exact rotation rate that remains only approximately known. And a ring system whose true age is still being actively debated using the very data Cassini risked its own destruction to gather. Cassini didn't end with one dramatic discovery. It ended by opening several scientific debates that, years later, are still actively being worked through, argued over, and refined by researchers who weren't willing to let a spacecraft's final, fiery plunge into a gas giant be the last word on any of it. In its final seconds, transmitting live, in real time, from inside the atmosphere of a planet it had spent 13 years studying, Cassini gave scientists more mysteries than it resolved, and in the strange calculus of real scientific discovery, that's not a failure. It's exactly what a spacecraft that flew closer to the truth than anyone had ever dared before was always going to leave behind.